Hello, good afternoon, everyone. Welcome to the lab class. According to the lab manual, I think, yeah, okay, thank you. According to the lab manual, it is experiment number 9. So, last week we did it experiment number 7, today experiment number 9. Experiment number 8 is a bit harder actually. I'm just trying to get you easy thing first. And this is the last week, so next week you will have a lab final, and it is in person. It is in a university, you already know it. So that means next week lab final. I will announce the syllabus on blackboard, and hopefully you will get the things. So definitely, okay, light brightness control, there is a sensor on the trainer board, the board that we used in some experiment, last few experiment, the microprocessor trainer board. And yeah, which day? In lab day, definitely on the lab day. So yeah, for all courses, lab final and final exam, they are on. Yeah, it is. I will say. I will decide it later. Okay, so it's not. Yeah, yeah. I will declare it on the blackboard. Blackboard. Okay. So just now concentrate on the lab today. So light brightness control by microprocessor. There is a sensor on the trainer board. It's called LDR. So it is LDR, light LDR. So LDR, it stands for light dependent resistor. So that means if light brightness, it change. According to the brightness of the light, the resistor value is changes. So for example, like if we have a resistor value changes, so okay, let us have a look. Simple circuit. Here it is a 5 volt, for example, 5 volt source. Okay, and we have a resistor through ground. Through resistor, it is connected to the ground. So what will happen if resistance value is changed? The current through it also will change. Okay, so so and the voltage, for example, across the resistor is output voltage. I mean, from from some part of the resistance value, it is coming. Okay, let us draw it again. Okay, for example, this is our 5 volt resistance, 5 volt source, and there is a resistance and there is another variable resistance. Okay, so this is the resistance, the variable resistance, it depends on the light. So if the light is more, the resistance value is more. If light is less, resistance value is less. Something like that, for example. This is called LDR. LDR. So the voltage, the voltage across the LDR, it also varies, because when the resistance value is more, then it will get the less I think. Okay, No, not this way. Circuit is another way. Okay, so that is a variable resistance. This is, for example, 5-volt input, and output is, this is the voltage. Okay, so now look at here. If R is bigger, you know, the R. So anyway, so look at here. If it is a variable resistance, actually the voltage across the resistance will varies, you know, according to the resistance value. So that means this variable resistance, it depends on the resistor. It depends on the light brightness. So LDR, it is a sensor, kind of sensor. So actually, you know, we know that there are different sensors, like temperature sensor, a thermometer. So voltage sensor, voltmeter, current sensor, ammeter, you know, speed sensor, tachometer. So there are different types of sensor. So one of the sensor, it is called LDR, light dependent resistor. It is actually a sensor, and it's a light sensor, light brightness sensor. Like if it is the middle of the day, it has a more light, more brightness, and so it gives a so actually, you know, the sensor actually sense the physical quantity in terms of voltage. In terms of voltage, then we calibrate it accordingly. Like, you know, for example, so a light dependent resistor, it actually uh, dependent on the light, it actually give us the voltage value. So voltage value, then we calibrate it. Like for example, if it gives 5 volt, that means it is equivalent to, for example, 100 lumen brightness, something like that. If it is unit is lumen, so kind of like that. So anyway, so a speed sensor, like speed sensor is tachometer, you know, motor speed, using the tachometer. So tachometer actually measure the speed in terms of voltage, then we calibrate it, like 10 volt equivalent to for example 10,000 rpm. 5 volt equivalent to 5,000 rpm. It's like it's so on. So you know, so main thing is so this brightness control. What is the purpose of today's experiment? Brightness control, automatic control. You know, like for example, in a room we have 8 lights. Okay, 8 lights, 8 bulbs or 8 lights. You know, when it is it is the middle of the day, when enough sunlight is coming to the through the window to the room, then I think these lights should be off. Okay, and when it is the night time, so there is no light coming from the outside, so light brightness is 0. Then what will happen? All the lights should be on. So it is the two I mean, um, uh, two different example. When it is full light coming from the outside, no, all the lights inside the house, inside the room, that should be off, because they have no use actually. But when it is night, it has the full use, and because no sunlight is coming. So yeah, it kind of like that. So that means this control, it should be automatic. So microprocessor actually perform this automatic action. So the problem is clear. Is it okay? Do you understand it? LDR, how actually, so that means this sensor actually it is used to sense the brightness of the light, how much brightness is there. Okay, so all right. So and other thing is, you know, like as the all the physical quantity, like I mean all the output of the sensor. So sensor is used to measure the physical quantity, like LDR is used to measure the light brightness. Thermometer is used to measure the temperature. Tachometer is used to measure the speed. Voltmeter is used to measure the voltage, current, so on. So all the physical quantities, temperature, pressure, light brightness, all the things are analog quantity, you know, they are analog quantity. But you know, computer system or digital system, it doesn't understand, it needs the digital quantity, not the analog quantity. So it needs a digital, so that then actually we have to use an analog to digital converter, ADC. ADC is a analog to digital converter. This is called analog to digital converter to digital. So we need an analog to digital converter, digital converter. Converter. Okay, analog to digital one, because all the physical quantity measured by the sensor, it is analog value. So but computer system, it needs a digital value or digital quantity. So that means we need an IC, analog to digital converter IC. So you I think this information you may get it in 370 or some other courses. What is how actually this analog to digital conversion done. So anyway, so analog quantity, it must be converted to the digital quantity. That means we have to use an analog to digital converter IC. So what will be the drawing now? Okay, let us go. Yeah. So first of all, let us discuss the basic thing first. And then this is here, it is a delay subprogram, we already know it for the machine, I mean the trainer board that we use. It has a 5 megahertz microprocessor, and for my 5 megahertz microprocessor, for 1 millisecond delay approximately, so 100 for 100 millisecond delay we have to load 27,300 or 2700. So here for 100 millisecond. So for 1 millisecond, it should be n should be 270. Yeah, this is the delay subprogram. All right. And then later on, so there is a flow chart. First of all, try to understand the flow chart. Okay, ADC, because as I said, we have to use an ADC. So if, for example, this is our microprocessor. This is the LDR. This is the ADC. Microprocessor here. And this is LDR. Okay, in between, for example, here we have, okay, Okay, so if we try to draw the block diagram of the whole things in a simple way, so what it is like that, you know, it is like that LDR. So LDR actually it sends the light, it says the light brightness inside the room or around it. Okay, sensor. And then as I said you, this is the analog quantity, but computer system it needs the digital quantity. So analog to digital converter, it converts this this IC, actually it converts this quantity to digital quantity, and then definitely we have given. So before, as we you know already, microprocessor normally do not directly connect it with the input output system, external system. It connects through 8255 IC, right? 8255 IC. So for example, port A used here to get this input data from the analog to digital converter. So port A is used to receive this digital data about the light brightness. So that means port A is an input port to get the and digital data of the sensor. All right, is it clear? And then so 8255 is connected to the microprocessor. This is the for example 8086 microprocessor. 8086. Is it okay? Do you understand these things? This block diagram, simple block diagram is okay? Clear? Okay, all right. And then you know that it actually okay, fine. And then it actually connected with because actually it's taking the okay, here is another port B. This is port B. Port B, it is connected to LEDs or lights. So think about the trainer board. LEDs are considered as a light. For example, they are light. They are lights. Okay, lights. So port B is connected. Port B is connected to the lights. You know, if the brightness is less, so it makes the light. Think about the situation like the night time. You know, there is sunlight, or inside the room is dark, or no sunlight is coming from outside. Room is dark. So it actually so a microprocessor through the 8255 port B, it actually turn on all the lights, and during the middle of the day it's fully full and room is full bright. So what will happen, so microprocessor keep all the lights off. Okay, so this is the two scenario, and in between it will work in between also. If the light is not the minimum or not the maximum, it will be in between, something like that. Is it okay? Do you understand these things? The flow diagram or block diagram, is it clear? Is it okay? Guys, is it okay? All right. So that means what actually we can see there here. Here, port A is an input port and port B as an output port. Okay. So port A is here to take the input data of the LDR, light brightness data, and port B is used to send the to turn on or off the lights. Like in our trainer board, it will be LEDs. Okay, and we consider it as a light in the so we are considering is in a small scale, just like the LEDs, 8 LEDs in our trainer board. You already know it. So they are, think about they are lights, 8 lights in a room. Okay, so now look at here. As so in this case, so this is the whole picture, whole that I mean things are in a short way using the block diagram. So this block diagram actually it's a complete picture of all the things. So if you do not understand, raise you. I mean, you should ask me now, or I will erase it. And you, what actually we have to remember it, that port A is used as an input port here, and port B is used as an output port here. Okay, all right. And as we are using the ADC, so there is some process. I mean, ADC, analog to digital converter IC. It has some characteristics, some features. So how actually it works, we should know it. So ADC, analog to digital converter IC, how actually it works, we have to know it. Okay, before I go to discuss about this whole things, actually I hope you already note it down, or you can remember it. Okay, then I will go for the next discussion. Because in this page, actually reading the ADC data, you can see reading the ADC data, how actually we can read the ADC data, analog to digital converter IC data. How can we read it? There is a just algorithm. This is called flowchart. You know that flowchart. Flowchart means the way actually we write our program, the way it works, and the way it works. Or yeah, first of all, what is the process of in our program, because this flowchart actually is important. We should know it, so that in our program we should write accordingly. We cannot we cannot overstep something, so for example, first do this, then the next, then but you cannot skip the first line, you cannot start from the second line, something like that. Okay, so how actually ADC works? First of all, actually, as it is connected to the port A, read value 1 from port A. First data, for example, first data you want to read value 1 from port A, and save this value, save this value 1, and read value 2 from port A, second data. Read the second data of the LDR, because it is connected to the port A. Read the second data, and then now compare the two values. If so, now this diamond shape, it is for the conditional check. In the flowchart, this is the flowchart procedure. So this diamond shape is for conditional check. Is value 1 equal to value 2? Is it yes or no? Value 1 equal to B. Okay, now look at here, because microprocessor, it works very fast, like less than a millisecond. It takes two data, first data, second data, and gap is very low, microsecond. So what actually the process is, it compares these two data. If they are equal, then, because the time gap is very low, almost zero. So if they are equal, that means it is accepted. If they are not equal, it will be rejected. It will not be accepted. So that's the thing here. If value 1 equal value 2, if it is yes, then actually it is accepted and return it. So that means from this subprogram will come out. Okay, so that means it is okay. It is return, or it's said we can say accepted. Accept value 1 on value 2, accept data. You can say accept data. Sorry, accept data equal either value 1 or value 2, because they are equal. Value 1. Okay. So if it is not, if they are not equal, because time gap is, I said, it is very low, 0, for example, time gap. So it takes two data in a 0 second gap, or close to 0. So if they are not equal, that means something, it is not accepted. So if it is no, then it will read again. It will do the process again. So if it is equal, then it accept data. So data will be value 1 or value 2. That's right. So is this flowchart is clear for ADC process, ADC data? Is the flowchart is okay? All of you okay? Is the flowchart is okay for ADC data? Because if it is clear, then it will be easy for you to write the code in the program. Okay, so this is clear, right? So again, I am repeating. Read a value 1. For example, a value. Read a data from the port A and save it as a save this value or save this data, and then within a, because the microprocessor, it works very fast, within a microsecond it takes another data, read another data 2 or value 2 from through the port A, because port A is connected to the port A, and compare these two values. If they are equal, if it is equal, accept it or return from this subprogram, because we will write this the code for ADC in a subprogram. So return from this subprogram or accept data equal value 1. And if they are not equal, do the things again. It is not accepted. So again do the same thing. All right. So this is about the ADC algorithm, or this is the flow chart. So this diagram is called the flow chart or program logic, you can say, for reading ADC data. Okay, now it's about the whole program. Okay, so whole program is, whole program, it is the flowchart is like that. Shortly we can write. Initialize. First of all, we have to initialize the program. Then we have to read ADC input data on port A. And now we will check if AL equal to 0 or not. Because this data, this port, so the AL, port A data, we read it in AL, right? What actually we do? We read the ADC data through like that, in AL, comma, port A, right? So for example, port A, in AL, comma, port A. So that means the accumulate on accumulator or AL register, the ADC data is there. Now we check if AL is 0 or not. If 0 means there is no data actually. If no, if AL is 0, so that means it is not okay. So we make AL equal to make forcefully 1, and then we will go next step. But if AL is not 0, that means it actually takes some data from from ADC, analog to digital converter, and then we have to divide this AL by 16. Why actually we divide it 16? Because we have to calibrate it according to the what. Okay, I will tell you why actually I said 16, and then add this. So result is saved in AL, because divide AL by 16. Actually, it actually perform AX divided by 16, and the result is saved in AL. Result is saved in AL. Now we'll add this AL to PTR pointer value, and so that we will get this we will get the output value for the table to the LEDs. Okay, and then we'll again start the things again and again. Okay, let us see what is the pointer, why actually we make it 16. Okay, let's see this table. Look at here is the table. For example, if we have 8 LEDs, all are on, then it will be FFH. If one LED is on and seven LEDs on, one off. For example, this is 1, 1, 1, 1, 1, 1, 1, 0. So all the LEDs on, just only one off. So it will be FE, or it may be FC. I mean, 2 off, that it becomes FC, or 3 off, it becomes F8, or become 4 off, it becomes F0, or E0, C0, is like that, or all LEDs. So look at here, what are the condition, how many situation we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 cases we have, right? 9 cases we have. So we have to adjust the value of the analog to digital converter with these things. When actually we have the minimum value, I mean, LED value, I mean, analog to digital value is minimum. For example, 0. Not 0 actually is not accepted. For example, 1 is minimum. Analog to digital value minimum. What actually we want? We want that means the light, it is the darkest time of the day. It is the night time. So all LEDs should be on. And when the analog to digital value is the maximum, the maximum value is like it's as it is a 8-bit data. So 100 and so 2 to the power 2 to the power 7 is what? 2 to the power 7 is 2 to the power 7. Yeah, 128. So 128. Okay. So look at here. We have a value. We have an analog to digital value 0 to 128. Okay. So 0 to 128. So that means the gap is around 128. But we have to adjust this thing with this 9 values. Okay. These 9 values or 8 values. So what will happen? What will happen if we divided it by 16? Around 16, you will get what? 128 divided by 16. It becomes 8 value, right? Around 8. 100. So that's why actually we divide this analog value divided by 16, we will get the 8 different values, and these 8 different values, because we have 8 different values of LEDs, we have to adjust it. You get my point? Is it clear why actually we divided this divided by 16? Is it okay? Yes, so that's why actually we divide the ADC value, because ADC value can be all 0, 0, 8-bit value, all 0, 0 means 0, and all 1, 1 means 2 to the power 7 is 128. So 128, so 128 different ADC value we can get, but we have to adjust because we have only 8 LEDs or 8 lights, for example. So 8 lights can have 8 different values, right? They can be all on, or 1 off, or 2 off, or 3 off, or all off. So around 8 to 9. Okay, this is actually all on 0. That means this is around 8 to 9. Okay, so to get 8 to 9, so for example, to get 8, we have to divide it by 16. So 128 divided by 16, you will get 8. That's why we divided by 16. Okay, so now now what will be the flow chart? Again, I am discussing this thing. First of all, we have to initialize like control what should be sent to the control register and what are the addresses. So these are the things we have to initialize, and then we have to read the port ADC value, and how actually we read it, we already discussed it in the previous slide, flow chart. So here is the flow chart for complete program. Then we check is AL is 0 or not. I mean the analog value in AL, is it 0 or not? If it is, if it is yes, if it is yes, we have to forcefully make it 1. Or if it is no, so what is the value of AL? What is the value of analog? We will keep it. And then we will divide it by 16, because to get 8 different values, because we have eight different combination of lights. So then this ADC values, after dividing by 16, we will add it to the pointer. The pointer value is the, the different light values. Okay, and then we will get, after adding them, we will get the what is the what value. I mean, the pointer value for this case is 0. What is the offset value? For example, this is the beginning of the offset value, then next one, then next one. We like it. So okay, so what is the pointer? Okay, pointer is the first offset value here, first offset value here. Then what will be the next one? The first offset value plus 1. So what is the next one? First offset value plus 2. What is the next one? Address first offset value plus 3, so on. Okay, so this is all the things in a simple way. Do you have any question here? If everything is clear, then we'll go for writing the code. All the process is clear. Any question do you have? No? Okay. Let us, yeah, now we will go to the program. Okay, let me open a blank. Okay, let us start here. So this is about the address. We already know it, that in the trainer board, the microprocessor trainer board that actually use in the lab, the addresses of the port A, port B, port C control registers are like that. Okay, so and what will be the control word? Okay, let us see what is the control word here. Control word. Okay, so this is 8-bit control word. So this one is first bit is for port C lower. Port C is unused here, right? It is don't care. And port B is an output port. So this is 0 and this is mod 0. And then this is port C upper. It is also don't care, because it's in this case only port A and port B use. And port A is for input port. And then this 2-bit for mod 0. And this is 1. So what is the control word now? We can see it is equal to 90 or 99. 90H or 99H. Is it clear? Control word is okay? Yeah, control word is clear? Okay, fine. Then, so let us continue our program. So control word is now written on the control register. Okay, now it's about the beginning of the program. So definitely we can write it as start. Okay. So this is the beginning of the, when actually it is a continuous process, we have to read. So control word we do not have to, we can write it as start from here, because when actually we'll read the process again and again. Okay, now it's about a start. So first of all, we have to read the, so this is the initialization. This is the initialization, we already done it. This is the initialize. Now it's about first of all we have to read the ADC. So ADC is analog to digital data. It is connected to the port A. So we call the ADC. We call a subprogram. Call ADC. Call ADC. And then we will compare it. CMP. Compare that AL, because in the main flowchart you can see the all the things in a main flowchart. We first of all we read the ADC. So call ADC another subprogram. Okay, so guys, wait please. Hello, assalamu alaikum, doctor. Yes, I am good. How are you? I am taking lab session, so let me feel 2 minutes. Okay, so I should come to your room. Okay, inshallah. Okay. So, guys, can you hold on for around 2 to 3 minutes, because Dr. Hussam, he called me. I'm coming back. Okay. So wait here. Wait, please. Okay, guys, I am back. So sorry, keep you waiting. And now we say that if we have to check that AL is 0 or not, because if you can remember on the flowchart, final flowchart, I mean that actually in a short way complete picture. Okay, AL is AL 0 or not? If AL is 0, okay, so we have to make it 1. Otherwise, we should keep what is the value of AL. Okay, so compare AL comma 0. If it is not 0, then come to a label, and if it is 0, then we have to make it 1. So move AL or AX. So AX1 means AL1 actually, doesn't matter. AX comma 1, and what is in the label L? H. So look at here, AL has the ADC value, okay? And what about the AH? AH, because we have to use, when actually we divide it by 16, we have to make it AX. So that's why we make AH 0. If it is not, I mean, because AH is our main value is in AL. So move AH comma 0, then we divide it by 25. So not 25, 16. So then move BL comma 16. Okay, let me make it little bit zoom out. Okay, and then move and division BL. So that means now AX is okay, AL equal AX divided by 16. Okay, all right. So this is in AL. Result is in AL. Okay, and now we do okay. So let us here. Okay, so we also write the table also. Let us write the table and the last end. Table. The table we have a D sorry DB or 0 FFH BB 0 FE H. I mean one light off, two light off, DB 0 F C H B B 0 F H H B B 0 F 0 H B B then 4 lights, so 1 3 lights all are off, just 3 lights on, so that means it becomes like 1 1 1 0. Okay, E so 0 E 0 H B B 0 C0H BB 80H and then BB 00H, and that's the end. This is the end. E and B, end. Okay, so this is our table. All right. This is our table. We write it here. The last time. Okay. So now before the table, so table and okay, fine. And we have to also write the ADC subprogram. Okay, subprogram ADC. Okay, so let us write the ADC also here. ADC. So this is the subprogram, for example. So what is the ADC process? Can you remember ADC? First of all, it is connected to the port A in AL, comma port A, and then we have to check it. Is so so this is the value 1. We have to save it. No BL, comma AL. So that means it is saved in BL. Then again we do the we read the data. So so before that, actually we do something for logical OR AL AL. Okay, I'll say it later. Then again we read the data. Move AL, comma port A. Okay, and then compare C and B. Compare AL, comma BL, because the value 1 is in BL and value 2 in AL. Compare them. So jump not 0. If it is not 0, if they are not equal, we do the things again. ADC jump not 0, it come again, it will do the process again. If it is 0 that equal, then we no. So I mean we can take this value. I mean it's okay. We can take AL, comma BL. So value 1, what was in value 1, we can save it in AL. Value 1, it's okay. This line is okay, or it is, you know, it's all right. And then return. Okay, this is the ADC process. Only the thing is here, what is the purpose of this one? This one actually to make the OR AL, comma AL. So it actually make the data. It's about the make the things error free or something. So this is not a big issue here. So the thing is, we read the analog to digital data in AL, and we save it in BL, and then we take again, we do that, we read the data again, and now we compare. So value 2 and value 1. So value 2 in AL actually. So AL, comma BL. If they are not equal, if they are not 0, that means come to the ADC. Or jump not equal. You can say jump not equal also. Jump not equal, it come to the ADC. Again do the things. If it is okay, if it is equal, then I think this line we can write it. I mean value 1, we can keep the value 1 in the accumulator and then return back here. Okay, now look at here, or directly value 2 also. Okay, now it's about finishing the program. Okay, so this is our okay, so then so we divide it by 16, and now we have to write move bx, comma, okay, let me write it in this line. EX, set table. So first data, what is the offset address for the first data? Okay, and then and yeah, I will discuss why actually perform the logical AND operation here, and then comma EX move SI comma AX, then A square bracket SI. Okay, and then out for B comma AL. Okay, okay, port B comma AL, and then EAR. Okay, look at here. So that's all. So so first of all, this is the initialization. This block, this is the initialization, and then we say that we have to call the subprogram for taking the analog to digital data. This is called subprogram. So okay. So now look at here. This is our this is our subprogram called ADC. So okay, we'll discuss it later. Called ADC. Then we compare that if AL and the analog value, if it is 0 or not. If it is 0, we have to make it 1. So if it is not 0, then come here. Not 0 means it is accepted. So AH just make we have to use the AX before division. So AH is 0 and AL is actually the actual data of the analog to digital data. And then move BL comma 16, that means because we have to divide it by 16. So then division BL, that means it is AX divided by BL 16, and it is actually a result in AL. Okay. Now move BX comma offset table. We have to get the offset address first offset address of the first data. What is the offset address of this one? Okay, so this is in BX, and then AND logical AND AX comma FFH. Why actually AX comma FFH? Because we have to actually, this is also to make the things more, I mean, error free, because AL has AL has the analog data, analog to digital data, the sensor data. So AX is our not point of interest. So what actually we do, we make logical AND with FFH. That means to make the thing what actually it is exactly. I mean, this is also not not important issue here. Same like here, this OR, just to make the things more error free or something like. Okay, then what actually this analog the scale down analog data, we will add it with this offset value, because if analog value is minimum, we have to make all the LEDs on. If analog values is maximum, then we have to make all the LEDs off. So how can we get this off? I mean, we switch according to this table. So after adding analog value, scale down analog value in AL, and then the offset address. So we have to add them together, and this add value we send it in a SI, and then move AL comma square bracket SI. So then we will get the LED's values. This will be, we will send it in the port B, and then jump start. We'll do the process again and again. And what is the analog to digital process? Analog to digital process is, first of all, we have to read the port A, where actually analog to digital data is connected, and then we save it in BL, this value 1, and then we read it again. So this is value 2, and then we compare them together if they are equal. If not equal, do the things, start again. If it is equal, then keep this value and return from here. So this is about all the program. So is it okay, clear, guys? Is it okay? So all right, so this is actually 3 line, you can see. If it is okay, then because this is one of, yeah, this is a simple idea. So think about the, make it a block. So first, this block is for initialization, and then this block is for initialization, and then in the main program we have to call the ADC. What is the block for ADC? ADC subprogram is this one. This one is the ADC subprogram. Okay, this one is the ADC subprogram. Okay, and then actually, and this is the table for 8 lights. Control, make the on and off. What is the data for 8 lights? Okay, and then how can we have all the blocks, we combine them in a main program? It is like that. So from start to here. So that's it. This is all about that. So clear, right? Any question here? Okay, so and then I will announce it on the blackboard. What will be the syllabus for lab final next week? This day, next week. So I will announce it on the blackboard, and we will have a lecture also. Tomorrow we will have a lecture. If you have a question, we will discuss tomorrow also. Okay. Any question here? Yes. Yes, Mokbil. I do not understand what you wrote here. What is your message? I do not understand. I already sent you email that when you are ready, just let me know. I will prepare the mid-lab exam for you. But it should be in person. So there is no but actually, you know. You have to come to the university this week. You come to the university and so I don't know. So if if you are not in Haferal, but then what can I do? Okay, so Yeah, so yeah, fine. You know that what is physical? So physical. So I mean, if you are not here, if you are not in, yeah. Okay. So any other question? So yeah, so you have to back because it is the it is the university decision. You know, lab final will be physical, and final exam also physical. And so lab final is next week, and final exam after that. You will get a schedule for final exam. So come to the university. This is the decision because it is not my job. It is not on my hand. It's the university decision. Okay, so you have to back to the university. Okay, all right, right? Any other